This is 405B running on Modal. So it's like write a poem about serverless computing. There we go. So you can tell it's slower than 8B. In the land of code where functions roam, a new paradigm dawned and servers went home. No more provisioning, no more scaling fears. Just write your code and let the cloud dry your tears. Maybe I've spent too much time on cloud infrastructure, but I kind of like that. Yeah, let me quickly just give you a high level of what we're going to do in this webinar. So going to walk through how to deploy an LLM inference service on Modal. Full-fleshed example, you should be able to just grab it and run it yourself. If you want to like fiddle with it, change anything about the way that what I do, you want to do something different. We're not just going to like deploy, set up the service and like hit it once. We're going to load test it as well to see like how well does this scale. We'll do that with Modal as well. Great. Let me start sharing my screen and we'll just dive straight in. I'm planning to just do this as like a terminal demo, live code, not like going through high-level slides. Maybe I should just give a quick pitch about Modal before we dive into full-on just code. So Modal's serverless infrastructure platform, you define Python functions, you describe the cloud resources that they need access to, whether that's 8 H100 GPUs or whether it's a distributed file system or distributed queue or whatever it is. You describe those resources alongside your code in Python, and then you send it to us. We run it, we scale it up, down, run it on a schedule, handle HTTPS security and things like that, so that you can focus on your code and we can focus on the infrastructure. So that's the overall pitch. You'll see that as we go through this like LLM inference example. This example, we're not just going to run any old LLM inference service. We're going to run an OpenAI compatible server. When LLMs first came out, kind of the thing people wanted to do was like send text in, get text out. And LLMs have gotten a lot like more capable since then. And now they do a lot more things. They don't just like complete a sentence or, complete a paragraph the way the initial completion APIs, and the way the models are sort of directly initially trained. They do a ton of other things like they do chat where they do multi-turn conversations. They produce structured output. And so the interface with LLMs has gotten more complex. If you are just consuming them via an API, if you're just using OpenAI or an inference as a service provider to run models for you, you don't have to worry about setting up that interface. They need to worry about it, and they have kind of all somewhat coalesced around this OpenAI API. Let's say you're already running an LLM app and you want to keep your same code. If you're using OpenAI models or an OpenAI compatible provider, you want to set that up yourself if you want to take control of your inference. And luckily, you don't have to roll that whole thing yourself. Just like you don't have to roll your own LLM inference engine, you can use an open source provider to define the inference engine and to define that API around it that's OpenAI compatible. So for this example, I'm going to use vLLM in OpenAI compatible mode. There's no restriction to running just vLLM models or to running just specific models of any given type on Modal, unlike inference service providers. We're just giving you basically like a Linux container that runs Python. So it's like very flexible, not like a specific particular framework. There was a question I already saw in the chat about why vLLM and not one of the other options. I think LM deploy, that's one people have been talking about. The other one that people talk about a lot is TRT LLM from NVIDIA, TensorRT for large language models. We have an example for doing that. That's also on our docs right there, featured in the sidebar. Check that out. You can get pretty excellent throughput with TRT LLM running on Modal. There's two reasons why we aren't doing it today. One is I think TRT LLM is definitely a lot harder to get set up. For a lot of people, the ease of use of vLLM wins out over what can be like a relatively small gain in throughput. Additionally, TRT LLM does not have an OpenAI compatible mode built in. You gotta write that yourself. You would maybe use something like NVIDIA Triton to turn TRT LLM into a web server or like a REST API, and then wrap that with additional methods to make it OpenAI compatible. So it's more effort than using the built-in OpenAI compatible vLLM, and I want to make sure to get through all of this in detail in the call. That's what I stuck with here. In general, I think you could check around. There's various people putting out benchmarks. The providers of these frameworks put out benchmarks. Other people put out benchmarks. You got to take a look what batch sizes are they using, what input token sizes and output token sizes are they using, and what does that look like for your workload so you can see how to choose between these. Let's dive into this example. I'm going to switch over from sharing a browser tab, which is where you can kind of like read the code and see it in this nice rendered way. I'm going to switch from that over to my VS Code. So what are we looking at now? On the left, my VS Code, I'm in that GitHub repo that was linked from the example we were just looking at. I'm in our LLM serving set of examples here. So we have other things. The TRT LLM example is there. We also have some stuff for serving vision language models. The thing we want to look at today is vLLM inference. So let's pull that up. On the right-hand side, we have the application on Modal. I've deployed this in the past, so it's on Modal as an application, but right now it's inactive. So there's actually nothing running on Modal. The service is not up. So let me show you what it's like to just quickly, like interact with that service. This example includes a OpenAI compatible client that can hit any OpenAI compatible backend. So let me run that script, start up a chat with it. All right, so this is starting that application that I've deployed to Modal. So if I take a look, we went from inactive to idle. So that's saying this thing is spinning up. And click in here to our logs. What's going on? Looks like, yeah, we have a pending request. We can see all the way there on the right. And then looking at the containers, we can see a container is now starting. Up until this point, no resources on Modal being used. So this costs $0 to run. Now we're starting up the inference service. Usually it takes about 30, maybe 40 seconds to spin up a vLLM inference server running one of these 8 billion parameter models. Maybe click in here and view the logs there. And let's drop that. And I'm going to zoom out a tad so that we can see a little bit more here. All right, so we've got those checkpoint shards are loading. We can see that we're like spinning this up. Oh yeah, we're also going to do some graph capturing. That'll take an additional maybe 10 seconds. But there we go. Now our service is spun up. We have like this one is just a little system prompt that says write poetry. So write a poem about serverless inference. Great, let's run it. Okay. So nice and like the 8 billion parameter model, this is running on an A100, so it's nice and snappy. Let's see, what poem did we get about serverless inference? In realms of cloud where code does roam, a mystical land of inference is home. Serverless, they call it a wondrous sight where compute's on demand, a magic night. Not great poetry, but this is only the 8 billion parameter model. Let's see, how does that get put up on Modal? What does it look like to deploy something like that on Modal? So looking over now up at the code section of my VS Code up here, so this one Python file defines the whole deployment of the inference service. There's one other component, which is like getting a hold of the weights. So there's any number of ways you could get a hold of the weights. You can download them from Hugging Face, elsewhere. We kind of separate that out, put it into this download llama file. This is another thing that runs on Modal, downloads llama and puts it in a distributed volume on Modal. So this is like a file system, but instead of it being like a disk attached to a specific computer, it's something you can attach or reach out over the network to from any Modal instance. So this download llama script, Modal run download llama.py, I can run that on Modal the same way I could do like Python download llama, or I could like enter into a cloud instance and run a script to download weights. So I already downloaded them, so that was super fast. So I didn't actually download the weights there. Takes a minute to get whatever 16 gigabytes of weights down. You run that to get that set up, and then from there, it's this vLLM inference script that sets everything else up. So we're using, so the specific model, AP instruct. I like to pin the model revisions because things do change, actually, especially right when the models come out. They can change pretty quickly. Usually they're fixing bugs with things like tokenizers, so it's worthwhile to update it, but you want to be careful not to leave that unpinned when you're downloading stuff. All right, now let's look at how we build the vLLM engine and serve it. So the way that works, just run modal deploy vLLM inference.py, and that'll set this thing up. So deployment just means like create this application, send it to Modal. The way you create an application on Modal is like pretty interesting. You take a Python function that does the work that you want to do. In this case, creates a FastAPI app that like runs LLM inference, and then you wrap it with some decorators. So the two decorators we need in this example is one, modal.asdi app that takes a function that returns a FastAPI app and sets it up so that we can hit it like over the internet, hosts it on Modal. And then app.function is this decorator above it. That decorator is there to like describe what's the environment that the function run in, what's the resources that it requires, how long does it need to run for, things like that. some relevant bits here. The container image, that's like, what's the file system state? What are some of the dependencies that you need? Let me scroll back up. I kind of jumped over that section up here. vLLM's nice, super easy to install. You just take a baseline Linux image like this Debian Slim, and then do a pip install that gets you vLLM and the CUDA stack that it depends on. With Modal, if you have a GPU running, then you have the NVIDIA drivers. You don't need to worry about driver level CUDA installation. We have a nice guide in the Modal doc for like the general CUDA stack and how CUDA runtime and CUDA drivers are different from each other. You do sometimes need to install some CUDA stuff. vLLM brings it in via a pip install, which is very nice and clean. Oh, there was one question about this Python version thing here. This is not mandatory. It's nice if you want to sort of make sure that you're always deploying something with the same Python version. If you don't provide this, it'll just deploy a version that matches the Python version that you're calling it from. But for production deployments, you probably want to pin that down so you don't get a different version if somebody else deploys the model. Chose 3.10 here, not for any particular reason. There are some speed ups if you go for the more recent versions of Python. They're working on some really nice improvements for speed. The nice thing about Modal is you wouldn't have to install that bleeding edge Python version locally if you didn't want to. You can kind of try it out and see if it's faster by changing that Python version. That's our image. That's one of the things that we decorate our function with. So it's a regular Python function, and we're saying this Python function should run in this environment that has vLLM installed, Python 3.10, and some like base Linux system dependencies. What else do we have here? GPUs, so your hardware requirements go in here. Usually you don't really need to specify CPU or memory because you kind of automatically scale to consume additional resources as you need them. So just that specifying the GPU usually suffices. For A100, you've got to pick 40 or 80 gigabytes. For the 8.1 billion parameter models, I found 40 gigabyte A100s like decent enough batch sizes, and just one of them is enough to run. As you get to the bigger models, you'll need more. If you look at that, the 405 billion parameter example that I shared, that one uses 8 A100 80 gigabyte GPUs. Some other things that we're specifying here, I'll talk about those once they kind of show up as I'm demoing. The last thing I'll say is like, this is where you would attach that the model weights that we downloaded. This volumes parameter here says, okay, I need access to this particular volume, this like Python object that represents the distributed file system, and then a path that it's available on the machine that is running the example. That decorator there is what turns this from a regular Python function into something that runs on Modal. There's some questions in the chat. Some of the other examples, download models to the image. Here you added it to a volume. Can we see speed improvements by using a volume? This is a really interesting question. Let me full screen my VS Code and say, like, up here, when we define the container image, we're really defining, like, what does the file system look like when your functions start running? And by attaching a volume, we're saying, like, oh, add this additional, file system in. So there's fundamentally, like, a trade-off or, like, a design point here, which is, like, where do I store information? Do I store it in the image, or do I store it in a volume? So they're backed by fundamentally, like, the same storage system. We use a lot of the same infrastructure under the hood. So there shouldn't usually be a very big performance difference. I think we used to have the image serving system used to be, I think, faster. And so we would encourage putting the weights into the image. I don't think that's any longer the case. The big reason to definitely use volumes instead of using images is if you want to be able to swap the model out really easily and change which model you're serving. If you're serving a bunch of adapters, individual fine tunes per user, you wouldn't want to make a new image for every single user. You'd want to retrieve that information live. So the more dynamic the information is, the more you'd want to put it in a volume instead of putting it directly in the image. Yeah, okay, let's want to keep going, make sure that we get through this entire example. So let's take a look at this serving code real quick here. Bringing in a lot of stuff from vLLM. So vLLM exposes the way to get a hold of an OpenAI-compatible server through a bunch of these components of the library. So I'm bringing all of those in. The import's inside the function here, because the fun fact about Modal is that the code that you have in this vLLM inference.py, the global level stuff actually runs twice. It runs once locally, where all it does is kind of define what needs to be run on Modal's cloud. And then the global scope, again, gets run a second time for deployment. So you don't want to put anything too expensive in the global scope. And then you don't want to put anything that can't run locally in the global scope. So my local Python environment is pretty minimal. I haven't installed very much in this Python environment at all. So I don't want to import vLLM in the global scope because that would run locally and then I would get an import error. So you don't always have to put it inside functions. There's a context manager that we provide to allow you to like include it in the global scope, but just not run it when it's local. Another pattern that I've actually kind of come to prefer is putting the imports inside of functions to say like when this function spins up, import all of these libraries. So that's why we've got all these imports here, and then bringing in FastAPI, the Python web serving framework, and vLLM. Let's actually maybe take a look at what this app looks like here. I created it. Paste. Get rid of that white space break that VS Code terminal introduced. Hate to see it. Okay, now we're spinning up that OpenAI-compatible server. Right, I redeployed to show you that deploy process. So now it's actually spinning back up again. So give that a second for it to load. And actually, what I want to go is actually not to the root, but to the docs. So nice feature of FastAPI is you get Swagger docs for free or OpenAPI docs for free that you use to look at what your routes are and use your authentication. As part of this demo, we like kind of show how to add middleware to that FastAPI app. So if you wanted to like customize the middleware, customize the way that the routes run, this is where you do it. vLLM actually does support this now. They will add authentication to the routes for you, but kept this in here just so you could kind of see what it would look like to add some middleware. So this is all FastAPI stuff. It's not particularly related to LLM inference, so I'm not going to go in detail through the code. The core thing is that we have these routers, these little route handler components, and we wrap those all up into this web app. And the last thing that we do is we need to attach an LLM serving engine to this web app, and that's this chunk here. This is the part, these async engine args are here's where you can kind of like tune the behavior of vLLM. For this example, I found I didn't need to do that much tuning to get what I considered acceptable performance. The main things that you're going to need to do are set up your model engine, set the tensor parallel size and the pipeline parallel size based off of how many GPUs you have available. This GPU memory utilization, you want to leave a little bit of VRAM aside for doing things like capturing CUDA to graph. That's what this line does down here. CUDA to graph, you can kind of like take a forward path through a neural network. That's a compute graph, a collection of nodes for operations and arrows between them to say this operation consumes the result of another. That's your graph. If you have a graph, you can go and optimize it. So it's kind of like a compiler path in that way. And this actually can speed things up quite a bit. CUDA graphs allow you to like avoid round trips to memory that can be kind of punishing. And you can also kind of combine CUDA kernels together, avoid kernel launches, which is also can knock into your GPU performance, cause you to wait on things happening on the CPU. This step here, it uses up some GPU memory. So I've got GPU memory utilization set to 90%. Another one that you frequently need to tune, the like max model length, how long can the sequences be? This helps set up your key value cache, the cache of the model's activations for past tokens. This determines what size it needs to be. Nice thing with vLLM, there's a lot of optimizations built into it that are just like not really visible here, like that KV cache and continuous batching to sort of like reconstruct the batch as you're going and serve inferences as they come in. That's sort of transparent here. We don't need to configure it. You can go a little bit deeper, and if you want to squeeze additional performance out of it, you frequently have to do so. But unlike TRTLM, in my experience, things have been acceptable without tuning those things carefully. So we create this engine and its configuration, and then that becomes our little OpenAI chat and OpenAI completion service. And then the last thing we do in this function is return the web app from the function. So return the FastAPI app. When this code gets run on Modal, on the machine that has the GPUs, that returned web app becomes a server. So speaking of which, there it is. These are the Swagger docs that allow you to interact with this as an API. So let's try and do a quick health check. Let's execute. Oh, not authenticated. That auth dependency that we injected says you need to be authenticated. The example just does it with a string, because it's intended to just be like a starter example. But you could set that, again, using a modal secret to inject information at like only available at the time when the thing is running, the same way you would handle like an API key, for example. Okay, so authorize, put in the super secret token. All right, we got a 200. Let me zoom in a little bit. guess the code doesn't get that big. But yeah, we can see we have a 200 on the health check. Nice thing to do when you redeploy, make sure that thing is ready. Okay, the bottom here just sort of describes how to interact with the server, which I already talked about, for example, running the chat client or checking out the docs route. One thing that was very recently added is this load testing. So you've got this thing running, you've hit it a couple times, but really what you want to know is like, what happens when I put this in front of users and allow users to hit this thing? There's this nice tool in Python called Locust that allows you to run load tests. So like stimulate traffic. So I'm going to hit modal serve OpenAI-compatible load test. Okay, so now we've spun up a new app on Modal. This is a different app from the LLM Inference, and this app will run the Locust load testing. So let me quickly, just so people see a little bit more about what that looks like. Looks like kind of similar basic flow. We create an image. This image now has what we need to run this load test. We don't need vLLM anymore. We need Locust, and we need OpenAI to run a client, but that's it. We need some files, like a description of what our load test looks like. Yeah, this is some configuration for that load test. And then there's kind of two ways that I've set up for this load test to run. What I'm showing you now is using modal serve to create this thing as a web server. So you go in and Locust gives you this nice UI for doing stuff. So let me start. Let's have one user who comes in. The user starts like chatting with the model, sends a request, and then like send something, then send something, then send something, like with I think 1 to 5 seconds in between. So now we're running. Requests are coming in. Takes about 5 seconds for it to finish. I'll go and I'll show you some metrics coming not from Locust but from vLLM in a second. We can see it takes a couple of seconds to finish the response to this individual user. So this is now running. That is this modal function here has created a little web server. So you don't have to use FastAPI or any like ASCII Python server. You can serve arbitrary web servers, anything that you can start as like a Linux process that listens on a port. And like we can serve that. So that's this thing here. Then alternatively, I also like this example shows you also how to run it as a script. So like if you just wanted to run a one-off load test where you would like configure things like the number of users coming in, and like how fast they come in, how many requests they do. So that's done with this app.local entry point down here, which is kind of like how you define the equivalent of a like main function, but for things that run on Modal. So yeah, so requests coming in, our load test is going, looks like it's staying at about 4 seconds. We only have one user, so that's not particularly surprising. So now let me scale this up. Oh yeah, good, no failures, good to see that. So fun thing about Locust in this UI is that you can edit the load test as it's going. So sort of like kind of dynamically change how users are coming in. So let's scale up to 100 users at 2 users incoming per second. That's now issued. We'll start to see the number of users go up in our logs. There we go. The users are coming in and requests start coming in. Let's now, while this is happening, let's go look at what's happening on Modal for this function. So we can see function calls coming in. I'm going to zoom out a bit, even though it makes the text a little bit harder to read, just so you can see this is the dashboard for our Modal app, and we can see function calls are coming in, lots of them. Now I'm going to zoom back in because we actually do want to read some of the text here. So there's one container that's live, and it's got 60 running calls. So 60 inputs have been sent to this to be backed up by vLLM and run, and for inference to run on them. So while this like scale up is happening, let me quickly. Oh, actually, I just saw something here, which is fun. So I set it up so that most of the requests don't get logged to the console because it would just be way too much. But you want to check because it's easy for things like LLMs, machine learning models, to like break in very subtle ways that aren't detectable with like they don't crash, they just kind of suck. You want to look at the examples every once in a while. You got to look at your data. So in this particular load test, I'm asking a model with a system prompt that says you are a modal salesman, and then I'm prompting it with the question each time, like, give me some fun date ideas. It's nice to have a little bit of fun when you're setting up this testing. So it gives answers like, it would be fun, uh, like set up a serverless, uh, automatic recipe organization so that you can do a cooking class with your partner. Great. So that's just a little bit of extra delight while we're load testing our server. Uh, so looking back at vLLM inference here, I'm going to scroll up and talk a little bit about this allow concurrent inputs piece. So allow concurrent inputs says when inputs come in, send them to this function, send them to the web app that this function is running, like send them to some like async IO running thing like what's under the hood with vLLM, send them in up until a certain point. Once you hit 100 inputs being managed by a container concurrently, like 100 or like backslash 100 effectively, then start scaling up a new replica and then send additional concurrent, like additional inputs that come into this other instance. So right now we have 100 concurrent users, but because they're like submitting stuff and getting responses and submitting and getting responses, we didn't go above 100 concurrent inputs. So we still have just one container. Let's go ahead and boost that up by a factor of 10 and make it 1,000 concurrent users. And we'll ramp up at, let's say, 3 users per second. So 3 new users will come in per second, start submitting requests. And how is our performance then? So as batch size goes up from 1, you're always going to see a degradation in performance with these. Like they are doing more work. It's not linear, which is kind of nice. Like you don't see like a linear increase in response time because there's lots of work that's amortizable, but you will see increased response time. So we've seen that. Looks like it's gotten a little bit slower than I would like. I would maybe tune this to a slightly smaller concurrent batch size or use a faster GPU because it's taking about 12 seconds to do a full response. If you look at the length of these responses here, they're in the hundreds of tokens, but so like if you were streaming, a user would get the first token faster than that. But that's still a long time to get the full answer to their question. And let's see, what did I want to show? Yeah, so to get an answer on that, like you might be asking, okay, what like tokens per second throughput are we getting? We can go and see those logs in Modal. And let's zoom out a bit again. And this gets logged. These logs are all streaming in. They're available super quickly. We can see that this is only like seconds ago. New ones will show up. Actually, let's show them coming up live. Logs. I don't know if you've used other serverless providers. One of the things that got me excited about Modal when I was initially a user was how quickly these logs showed up, how quickly I could like find bugs because of that. And let's go back to searching for metrics. What are we seeing? All right, seeing on the order of, see, these are old. Let me make sure that I get to a point where we're full batch size. Okay, we've got 100 requests on this particular replica, 350 tokens per second, and output throughput of 1,800 tokens per second. You could definitely speed this up. I haven't like taken the time to increase that throughput. Because there's kind of 2 ways that you can run high throughput LLM inference, right? There's one thing is making your individual replicas of this service, your individual instances need to scale up. You need to make those faster. So you could probably boost this up. Like you could put this into FP8, like this is FP16. And you could do additional work on tuning that engine. You might be able to get slightly higher performance than vLLM by using another serving framework. They kind of trade off on who's fastest. So you can boost that, but separately from that, there's going to be a limited amount of capacity that any one instance is going to have. And so the other way to scale high throughput LLM like inference is to increase the number of replicas. So as we've been scaling up, and more users have been coming in, new containers have been coming in. Every time we get 100, every time one of them fills up with 100 inputs and we start to get pending inputs, we scale another. So that's set by that allow concurrent inputs value. So that's why we have 5 live containers and about 500 running inputs. So now 6 containers are live, and so now we can run 600 inputs. But there's even more users coming in. So even though we slurped up all 600 inputs, new inputs came in, and now they're waiting in a queue. and that's going to add to the time that users need to wait, both time to first token and latency to complete the request. And so now Modal will start spinning up an additional instance. Let's see how that looks on our locust chart here. I did kind of pick the numbers kind of carefully here. The speed at which users come in is roughly the rate at which new replicas spin up. So it's about 100 users show up in 50 seconds, and it takes us like 30, 40 seconds to spin one up. And so we actually are seeing that even as the requests per second are going up now, we aren't seeing an increase in the response time in the 95th percentile or in the average. So once we started to get multiple replicas going, we aren't seeing those tail latencies anymore, and we've like flattened out at about 18 seconds to respond. So this is the fundamental thing that I really wanted to get across here, which is like, what is it that Modal brings to an LLM inference service that is particularly special? It's that in addition to having it as Python code that you control, that you run, and like not like an inference service that is run by somebody else, alongside that, you define the like infrastructure that you need, and that like all from inside Python, and then that will scale up with your usage. And so when you're like, 50 people hit your demo at once because you're showing it at a meetup, or you get to the front page of Hacker News and a bunch of people show up, then you won't suddenly experience like 50-minute queues, right? If like all of these 1,000 users were all hitting one replica that can only handle a batch size of 100 at a time, then people are going to be waiting like 10 times longer during this period. And right now, like with our full scale up, we're only waiting, 50% longer, maybe less than people were waiting before. And so this is an independent axis for like scaling up your LM inference, besides what people normally think about, which is like, how do I get more juice out of those like A100s that I'm paying for? Or, how do I squeeze this model down smaller? And these are orthogonal axes for improvement. Many, if not all, of the things that you do to like improve the performance of an individual replica will also improve the performance of this overall system. So let's see how we're doing here. We finished our scale up, and now we've got 9 replicas handling 800 and some requests at a time. They're all staying live because they're all getting requests, and we see things still coming in. Was there anything else I wanted to show from the load test? Oh yeah, Locust is nice. I do like Locust. This is back when state of the art was serving computer vision on AWS Lambda, was when I discovered it as a tool for load testing LM services. I really like this web interface that we have here. Is not just when you're live serving things, it's also you can like get a hold of this report, download it, like share it with people. You could serve it on Modal if you wanted to like serve it offline, like via FastAPI service that people can come in and check results that you ran separately. And the load test script is designed to set that up. It saves, in addition to saving like weights and big files on volumes, you can also like save things like this test report and then go and access them later, which is great. I've lost a lot of really great like logs to ephemeral instances, so it's great to have that. All right. So let me go ahead and I'm going to stop sharing and take a look at some of the questions here. Question from Charles Pierce: the metrics of tokens per second account for concurrent containers. I imagine that is per container, right? Yes. So those tokens per second metric, when I quoted that, which was like 1,500, 1,500 tokens per second. Yeah, that's being reported by vLLM, and that's coming from inside a container. So you'd have to aggregate those values if you want to know your total tokens per second. What's useful of having those per container level ones is like your spend is going to be per container. Your spend is going to be how many resources are you consuming for Modal, so how many containers. So so improving the like individual replicas is going to be a great way to drive costs down. And then like once you have that, you can then transparently scale it up using something like Modal. Mayank saying, from a practitioner's perspective, this looks cool. Thanks, Mayank. Question from Abhishek: I have predictable load like LLM evaluation kind of works. How can I maximize my throughput for such cases? Should I skip FastAPI server, directly use vLLM? Yeah. So the TensorRT LLM example is like a little bit more oriented to this high throughput, like very like a big batch comes in that you control, like LLM eval. So that shows the patterns, like modal patterns for that, but it's in TRT LLM. Actually, with big batches, what I have seen and what I've heard from others is that the larger the batch size, the smaller the difference between vLLM and TRT LLM. It matters less which one you choose. Whereas at the low batch sizes, there can be some latency differences. But yeah, I would check the TRT LLM example out for that. Oh, also the vLLM code base, like they share how they can run OpenAI's like batch interface for for a LM server, the thing where you can like send stuff and get back a result within 24 hours, but not live. So that's kind of an interesting one. I haven't looked into that. Let's see. So I'm going to scroll up and answer some earlier questions. Speaking of concurrent users putting across multiple users, how would prompt caching work across the replicas? Yeah, so prompt caching, where you kind of like store the key values for like a particular prefix, the simplest thing to do is to just like recache the prompt every time you spin up a new replica. That will incur some cost. The shorter the prompt, the more that makes sense. If the prompt is super long, then you might actually just you might like persist the prompt cache to disk or to a modal volume and then read that prompt cache in another replica. If it's faster to read it from disk than it is to recalculate it. But yeah, so there's some things where you speed up a service by doing amortizable work like caching a prompt. And when you spin up replicas, sometimes you need to repeat that amortizable work. Generally, the technique for handling that and making sure it doesn't cause increased like P95 latency, like what happens to the poor user who has to wait on your prompt cache? The solution for that is something that Charles Pierce brought up, volumes and wrapping functions inside classes. So in Modal, we give you the ability to control sort of the container lifecycle with this modal.cls or class. I like to say that CLS actually stands for container life cycle because it's about what happens before a container boots up, what happens while like a function is running, and what happens like when a container spins down, the function is done. So you would put something like prompt caching if you wanted to make sure that you don't have like random spikes in latency for some users, you would move that into the entry. So then a thing wouldn't finish cold starting until it had finished that loading. So Charles's question initially was about volumes and whether they mitigate the need to use that like cold boot. And I think the answer is that volumes generally just allow you to access like attach distributed file systems to your modal workers, and they don't like you will frequently want to like read something from a volume during that like entry phase before the container is fully booted. Akash Sonowal asked, is async vLLM client needed for continuous batching? Yes, I'm pretty sure that's the case. I haven't tried to do it otherwise. I'm almost positive that that is true. So I don't know how you do it without coroutines, but I don't know the details of how it's run. Maybe I'm wrong. If anybody knows more about the internals of vLLM than I do, post it in the chat. Does vLLM handle structured decoding for JSON? Yes, this is from Connor. vLLM supports outlines. Oh yeah, Kayvon has already said this. And there are an OpenAI compatible serving also includes like grammar guided generation. So like you can control the behavior of outlines from your client talking to your OpenAI compatible server, which is very sick. Can we run a modified vLLM? Because we've done some optimization to vLLM for our workloads. Hell yeah. So you could install from a private repo. I just pip install vLLM, but you can git clone something and then pip install a local file, or you can install from a private repo. You can bring your own Docker image if you want. We have some optimizations to make Docker builds faster on our end and like better caching. But if you want to build your container images elsewhere, you can do that or hand us a Docker file. So it can be like any code you want. That's the vision with Modals, like totally generic infrastructure. So another question from Akash. Unlike K8, does Modal support replicas on a single GPU node? K8 can, to some extent, do time slicing, and does Modal do the same? So we actually had type slicing in the past, kind of where like you would expose like a fraction of a GPU to people, and it turned out that people didn't want it that much, but we could bring it back. The way I would do that as a modal user right now is I would run something like NVIDIA Triton that like takes a whole GPU and chunks it up, right? And like runs multiple copies of models. Like this dates back to the time when models were kind of smaller. You could run more copies of them inside the VRAM of the like largest GPUs. That would be if I needed to run multiple models within a single service. I would probably reach for NVIDIA Triton or something similar to NVIDIA Triton. New question just came in. I have a C++ and PyTorch code base. Is it possible to run training using Modal? C++ involved the training to generate data? Yes. So you'd have to like kind of run the C++ code from Python. So that like what that generally looks like is like Locust is a command line tool. I don't know what it's written in. I guess a lot of it is written in Python, but that doesn't really matter. From Modal's perspective, Locust is something that you call from the command line. So you just like open it as a subprocess, run it. So that would be the way to do it. If you have Python bindings to that C++ code, then you can like use it like more programmatically, like import stuff and run functions rather than like calling via subprocesses. But in general, like running training on Modal works super well so long as you can fit your training inside 8 GPUs. So like 8 H100s, because it's like we're working on some distributed training stuff, but it's kind of challenging to do distributed training fully serverlessly. So it makes most sense for maybe scaling up 8 H100 training to like a giant hyperparameter suite that like transparently scales on Modal. So I think this was officially set to end at 12:50 my time, which was about 5 minutes ago, but I'm going to stick around for 5 more minutes. One thing I do want to show you, some people were asking about 405B. I shared some code for doing that. I'd say with 405B, it is to the point about like you want to have a workload that fits in 8 H100s or 8 A100s. You can run 405B on Modal, but you want FP8, the 8-bit floating point version. vLLM released actually a very good 8-bit floating point quantization with like pretty high recovery of capabilities. So let me just show you that real quick. So the same example that I just ran with 8B works with 405B with like, change the GPU request. This is 405B running on Modal. So it's like write a poem about serverless computing. There we go. So you can tell it's slower than 8B. In the land of code where functions roam, a new paradigm dawned and servers went home. No more provisioning, no more scaling fears. Just write your code and let the cloud dry your tears. Maybe I've spent too much time on cloud infrastructure, but I kind of like that. Let me look at the questions for a second. Does Modal provide a debugging SSH in case things go terribly wrong and unfortunately have to debug it on there? Yes, we want to make sure that that's the case. Let me actually just Modal shell into which one? Let's Modal shell API.py. Oh, that is going to request 8 A100s, which is going to cost me a couple bucks to show this demo. And it might take, with 8 A100, 8 gigabytes, there can sometimes be a queue for Modal resources. So that, timed out waiting for the sandbox. So that's a bummer. But we can Modal shell into the load test. That one should definitely work. So sometimes you have to hit it a couple of times to get in. You can also like kind of container exec things, and that should be a little bit more reliable than the interactive shell for the case of these like super high resource requests. So now we're on that load test one. This is the one that runs that load test. We can look, what is the exact locus file.py that's running there? You want to debug it. So I like that. Like when I'm setting up examples, when I'm setting up stuff on Modal, I'll frequently do stuff via the command line and then translate it to Python afterwards. So it's a feature I use a lot. And I really appreciate the speed on that. And that would be a great place to end it, but I can't resist answering this question from Kevane. Is there a risk the bots could find the endpoint as it's open and keep the expensive GPU warm, even if they failed authentication step in the FastAPI middleware? Yeah, so the structure of this one is not designed to avoid that problem. It's like designed, a little bit for simplicity. Like you could introduce an additional hop where you run a FastAPI server that just does auth and then submits requests. And then you could even do it, like you do the request not via HTTP, but using Modal as an SDK. And we use RPC, so there's like, it's like maybe some speed benefits. If you're on the Modal Enterprise plan, you could pin those resources to live in the like same cloud environment. And because they live in the same, like, not necessarily same data center, I think, but at least close enough that you aren't waiting like, you aren't adding like hundreds of milliseconds of additional latency, like maybe 10. So that would be the solution to try and avoid like bots forcing you to stay warm just to say no to requests without tanking your latency. Thanks everybody for the kind words. I answered all the questions that I saw, tried to answer everything. If I didn't answer your question, I apologize. Hit me up on Twitter. My DMs are open, or in the Modal Slack. Yeah, if you post in the Modal Slack, Eric or Akshat might answer your question. The folks here are like pretty aggressive about supporting user inquiries. So definitely post there. That's modal.com/Slack. Thank you so much for coming, and I hope to see you at future webinars, at future events, and to see what you build on Modal. Take care, everyone. Bye.
We're cooling up a storm with